So we're going to move on to section 1.2, but we're still going to be talking about functions. We're going to go over a couple of quick vocabulary words, and then we're going to talk about how to use some of the basic algebra that you are familiar with to answer questions about functions and just figure out things about functions and their graphs. The first word, a point where a graph intersects the x or y axis, is called an intercept. And again, you've heard that word before. Not an intersect, it's an intercept, like an interception. An x-intercept occurs when y equals 0 and can also be called zeros or roots. A y-intercept occurs when x equals 0. And if you look over here very quickly where it says an x-intercept occurs when y equals 0. So if we look at these points, all of these points are where there's an x value and a 0. And then this could be x2, 0, and this could be x3, 0. But all of them have a 0 for the y value. And just the same, the y-intercept occurs where x equals 0. Right here, this point would be 0, comma, y. And notice for the x's, I had an x1, x2, x3. But for the y's, I just have a y. And that's because a function can have multiple x-intercepts, but it can only have one y-intercept. And hopefully that makes sense to you, that if we had a function that had multiple y-intercepts like this, then it wouldn't be a function because it would fail the vertical line test. So a little connection there for you, hopefully. We're going to start right away with doing examples because that's the easiest way to see how this works. We're going to find the y-intercept and we're going to find the x-intercept, both graphically and algebraically. So we'll start with the y-intercept and we're going to do graphically first. So when I look at this graph, I can see right here that that's where the y-intercept is, and it looks to me, and I'm just guessing, that that y-intercept is about 1 1/3. So we'll say that point is 0, comma, 1 1/3. And then I'm going to look at the x-intercept, about where I think it is, right there. And that also looks like it's about 1 1/3 past that first one. So again, graphically, we're not going to get exactly right. We're just looking. So I'm going to say 1 1/3, 0. Now, algebraically, we're going to be able to figure out exactly what these are. So we know we have our function here, f of x equals negative 2x cubed plus 4. Well, to find points, x's and y's, we're going to write y equals negative 2x cubed plus 4 divided by 3. And we're going to start out with, I'll just start with the y-intercept. To find the y-intercept, let's look back up. It says the y-intercept occurs when x equals 0. So I'm going to take my function, my y equals negative 2x cubed plus 4 divided by 3. And everywhere that there's an x, I'm going to plug in a 0 because I know that a y-intercept occurs when x equals 0. So y equals negative 2 times 0 cubed plus 4 divided by 3. Now I do the 0 cubed first, so 0 cubed is 0. 0 times negative 2 is 0. So I have 0 right here, plus 4 divided by 3. So 4 divided by 3. And that would make my y-intercept be the point 0, because x was 0, I plugged it in, 4/3. And hopefully you recognize that 4/3 is the same as 1 1/3. So we did a pretty good job with that one. Now let's go and look at our x-intercept. Again, we have the same equation. But the x-intercept occurs when x equals 0, y equals 0. So the way I do this is I make the y a 0, and I solve it. So I'm going to subtract 4 from both sides. I get negative 4 equals negative 2x cubed. Divide by negative 2. Okay, then I have x cubed equals 2. To get rid of the cubed, I'm going to take the cube root of each side, and I'm just going to be left with the cube root of 2 equals x. Well, I don't know what the cube root of 2 is. I'm not a calculator, so I'm going to put that into my calculator and find that x is approximately 1.26. And if you don't know where to find that on your calculator, you hit the math button. So to do the cube roots, you do math, and then there's the cube root button, or cube root is one of the options right after that. So this is the point 1.26 comma 0. Now look back over here. I estimated that it was 1 1/3, which is 1.33. 1.26, that's pretty close, so I feel good about that. I found the y-intercept and x-intercept both graphically and algebraically. So for this problem, we are done. So let's move down to this g of x problem. This is g of x equals the absolute value of x minus 5 minus 1. So let's go again. Let's start with graphically. Remember, we're finding the x-intercepts, y-intercepts, graphically and algebraically. So graphically, I'm going to look for, let's do y-intercepts first. So y-intercept is right there. And this is my origin 0, 0. So 1, 2, 3, 4. I say that my y-intercept is 4. And so that's going to be the point 0, 4. And then I'm going to do my x-intercept. So x-intercept. 1 right there, 1 right there, 1, 2, 3, 4. So it looks like 4 and 6 are my x-intercepts. So that would be the point 4, 0 and 6, 0. So again, algebraically, I have this equation. This y equals the absolute value of x minus 5 minus 1. So, just like last time, I'm going to start out looking for the y-intercepts first. And y-intercepts occur when x equals 0. So, I'm going to rewrite this equation. Y equals the absolute value of 0 minus 5 minus 1. So y equals the absolute value of negative 5 minus 1. And you know that absolute value makes things that are inside the absolute value positive. So this is just 5 minus 1. So y equals 4. And just like my graph showed me, y equals 4. So I feel good about that. So go ahead and put a box around that one. And then we come over here, we'll do the x-intercepts. And remember, for the x-intercepts, the y has to equal 0. So we're going to write 0 equals the absolute value of x minus 5 minus 1. So we start solving this. We get 1 equals the absolute value of x minus 5. And hopefully you remember from our algebra review that anything that's inside an absolute value can either be the positive or the negative of whatever it equals. So we're going to say that x minus 5 equals 1, or x minus 5 equals negative 1. Because if this added up to negative 1, the absolute value bars would make it positive and we'd be good to go. So we're going to add 5 to both sides and get x equals 6. Same thing over here, add 5 to both sides, and we get x equals 4, which is exactly what we thought when we looked at the graph, so we know we're doing it right. So this is the point 6 comma 0. This is the point 4 comma 0. And we found our x-intercepts and y-intercepts. We're going to look at a couple of things that you're probably familiar with from geometry, something called symmetry. Now, The graph of a relation or a function can be symmetric to the x-axis, where it looks like the x-axis kind of splits it in half, and you could fold it over on top of itself. It can be symmetric to the y-axis, where the y-axis splits it in half. And it can also be symmetric to the origin, where it looks like if you folded it in half this way, and then you folded it in half again down that way, the pieces would match up. So there's real quick, easy ways to tell without actually having to graph things, whether or not they're symmetric to the x, y, or origin. To tell if a relation is symmetric with respect to the x-axis, all we have to do is replace y with negative y. And when we do that, if replacing y with negative y produces an equivalent equation. And you'll see what that means in a minute. It's real easy. You'll pick up on it real fast. To see if something is symmetric with respect to the y-axis, we replace all the x's with negative x, and if that produces an equivalent equation, then we know that we're symmetric to the y-axis. And lastly, symmetric with respect to the origin occurs if we replace x with negative x y with negative y, and that produces an equivalent equation. Okay, so we're just going to do one of these for a quick test here. Example 2 says use the graph of each equation to test for symmetry with respect to the x-axis, the y-axis, and the origin. So we're going to test all three just so you can see how it works. Now, graphically, because it says use the graph, so anytime it says use the graph, you should use the graph. So graphically, what do we see? We look at this picture. It looks to me like this graph is symmetric with respect to the y-axis, to the x-axis. So I'm going to write that down. Symmetric with respect to the x-axis. Algebraically, we need to test this and make sure it works. And I know when you look at the picture, you're like, well, of course it works. I could fold it in half. But just bear with me because they're not always going to be that easy. So we have our equation, x minus y squared equals 1. So first we're going to test if it's symmetric with the x-axis. So we have x minus y squared equals 1. And what I'm going to do to see if it's symmetric with the x-axis, remember back up here, I'm going to plug in negative y everywhere there's a y. So I'm going to write x minus negative y, replacing y with negative y, squared equals 1. And I'm going to work on this, but this is where your order that you do things is really going to come into play, because if you say negative and negative makes positive, you're going to make a mistake here. So this is x minus, remember, parentheses, exponent, multiply, divide, add, subtract. So we're going to do PEMDAS. So the first thing we have to do is the parentheses and the exponent. So negative y squared is positive y squared. And that equals 1. And then we look, is this equation that we started with the same as the new one after we substituted a negative y? And it is. So we are symmetric with respect to the x-axis. And just so you can see it fail, we're going to do the y-axis. Okay, so we start with our x minus y squared equals 1. And we're going to do the same thing we just did. except to test for symmetry with the y-axis, we need to plug in a negative x. So we're going to do negative x minus y squared equals 1. Now, there's no more simplifying we can do. I can't reorder this in any way. I can't factor anything out. You can get creative with these and try to move stuff around. Like we could take out a negative 1 and have x plus y squared. And then we could divide both sides by negative 1. We could do all kinds of stuff, and we could spend all day manipulating this, but we're never going to get it back to looking like this one. And this will happen. This usually happens really quick. So if you can't tell within the first couple steps that it gets back to the original equation, then you know that it's not symmetric to the x-axis, to the y-axis. And so the last one we're going to check is the origin. And we're just doing this for a kind of so you can see how it works. We'll do x minus y squared equals 1, and it said if we're going to have symmetry with respect to the origin, then we need to replace all the x's with negative x and all the y's with negative y. And if we can produce the original equation, then we're good. We have symmetry with respect to the origin. So this is negative x minus negative y squared is y squared. And this is starting to look a lot like what we had up here. And we could do all that manipulation, but we're never going to get it back to what we need it to be. So this one also is not symmetric with respect to the origin. Now it might seem to you like that was a big waste of time because this says x-axis. I look at the picture, I can see it's on the x-axis. It's pretty basic. But you may not always be able to graph something, or the graph may be very complicated and very time-consuming to produce, and it's a lot faster just to plug this stuff in and check these things real quick. So there's 2 more examples on the next page. I want you to try both of those. So try to determine if they're symmetric with respect to the x-axis, the y-axis, or the origin, and do all 3 tests, and also say what you think they are graphically. And that is it for functions and symmetry.